Listen to the ambient sound of a modern commercial airliner in cruise. It is a steady, reassuring hum. To the passengers sitting in the back, reading magazines, or drifting to sleep, it is the sound of absolute safety. But inside the cockpit, a routine descent through clear night skies can change its nature in the blink of an eye. There is nothing unusual on the weather radar. The radio chatter is standard. And then, a single digital number on the primary flight display changes. A visual cue shifts. An amber light blinks. 800 feet, 500 feet. Traffic, too close. The human heart rate spikes, but the training takes over. In aviation, a catastrophic disaster rarely happens in a single violent instant. It is almost never just a wing falling off or an engine simply stopping. A true catastrophe is an incredibly complex chain of microscopic events. It is a slowly building sequence of minor mechanical anomalies, slight communication delays, deeply hidden human errors, and incorrect assumptions made under extreme fatigue. But sometimes, literally in the final few terrifying seconds, that chain is violently broken. Something shifts. Someone looks out a window. Someone pushes a throttle lever. Someone defies the rulebook. Today, we are looking at 4 heavily documented aviation incidents that mathematically, mechanically, and logically should have ended in unimaginable tragedy. But they did not. These are the flights where the invisible margin of error was reduced to practically zero, and disaster was averted not by luck, but by the absolute limits of human ingenuity. To understand the absolute peak of human aviation survival, we must first go back to a bright summer afternoon over the American Midwest and look at a machine that lost its fundamental ability to fly. Commercial airliners are flown using hydraulic fluid. The pilot moves the control yoke, and high-pressure fluid acts as the heavy muscle, physically moving the massive ailerons, elevators, and rudder panels against the brutal aerodynamic force of the wind. A heavy wide-body jet like the McDonnell Douglas DC-10 has 3 completely independent, separate hydraulic systems. The engineering logic is simple. If one fails, you have 2 backups. If 2 fail, you have 1. The odds of all 3 failing simultaneously are mathematically considered to be 1 billion to 1. It was considered an absolute impossibility until United Airlines Flight 232. Cruising comfortably at 37,000 feet, the massive fan disc inside the tail-mounted number 2 engine suddenly catastrophically shattered. This is known in aviation engineering as an uncontained engine failure. Heavy, razor-sharp pieces of titanium shrapnel blasted outward at supersonic speeds, tearing through the tail section of the aircraft. By a twist of unbelievably cruel physics, that titanium shrapnel severed the lines for hydraulic system 1. It severed system 2, and it severed system 3. In a matter of seconds, all of the highly pressurized hydraulic fluid bled out into the cold atmosphere. Inside the cockpit, the flight crew was suddenly wrestling with a dead yoke. The control columns were completely slack. The massive aircraft began to bank heavily to the right, slowly initiating a death spiral toward the ground. When a multi-million-dollar aircraft loses all flight controls, there is no checklist. The manufacturer never wrote a manual for this scenario because it was deemed impossible. But the sky does not care about statistics. The captain, Al Haynes, and his crew realized they had only one singular, desperate tool left at their disposal: the 2 remaining wing engines. By pushing the left throttle forward and pulling the right throttle back, they could use asymmetrical thrust to force the aircraft to slowly turn. By pushing both throttles forward, they could increase airspeed and create lift, pitching the nose up. By pulling them back, the nose would drop. An off-duty training instructor named Dennis Fitch happened to be in the passenger cabin. He walked up to the flight deck, stood behind the captain and first officer, and literally operated the throttle levers with his bare hands, manipulating the roaring engines to keep the wings level while the pilots managed the radios and navigation. They fought this violent, uncontrollable heavy machine for nearly 45 minutes, steering it toward a runway in Sioux City, Iowa. The landing was unimaginably brutal. The aircraft hit the concrete at nearly twice the normal landing speed, completely uncontrollable in the final seconds. The airframe broke apart and erupted into a massive fireball, tumbling down the runway. But because of the astonishing improvisation of the crew, because they used the physics of thrust to solve a problem of lost aerodynamics, 184 people walked away from an impact that should not have had any survivors. They proved that sometimes aviation is saved not by following the emergency protocol, but by the sheer, unyielding intellect of the humans sitting in the forward seats. But sometimes the machinery works perfectly. The engines purr. The hydraulics hold pressure. The computers calculate exactly what they are supposed to calculate. And the catastrophic threat comes from a deeply flawed human assumption. Fast forward to the night of July 7th, 2017, over the dark, sprawling urban grid of San Francisco. Air Canada Flight 759, an Airbus A320, was completing a routine flight from Toronto. It was close to midnight. The crew had been awake for a very long time, and their circadian rhythms were dragging them into a state of deep biological fatigue. They were clear to land on San Francisco runway 28 right. As they broke through the scattered clouds and looked out the windshield, they saw parallel lines of bright lights stretching into the darkness. To their exhausted brains, the visual picture made perfect sense. The line on the left must be runway 28 left, and the line on the right must be their assigned runway 28 right. They visually aligned the nose of their aircraft with the lights on the right, disconnected the autopilot, and continued their descent. But their brain had created a terrifying optical illusion. Runway 28 left was actually closed and completely dark. The lights they thought belonged to the left runway were actually runway 28 right. And the lights they were currently aiming at did not belong to a runway at all. They were aiming directly at Taxiway Charlie. A taxiway is the slow-speed concrete path where aircraft wait their turn. And on this specific night, Taxiway Charlie was acting as a parking lot. 4 massive, heavily loaded wide-body passenger jets, carrying over 1,000 human beings and hundreds of thousands of pounds of highly explosive aviation fuel, were sitting nose to tail on that taxiway, waiting for clearance to take off. The Air Canada pilots were descending an incredibly heavy metal machine directly onto the roofs of these parked aircraft. Inside the dark cockpits of the planes sitting on the ground, the crews looked up through their windshields and saw a terrifying sight. 2 brilliant, blinding landing lights were dropping directly out of the sky toward their faces. An incredibly tense voice from a Philippine Airlines pilot on the ground cut through the radio frequency, asking air traffic control where this guy was going. In a local control tower, the controller squinted at the radar, looked out the glass, and realized the monumental horror of what was unfolding. He immediately grabbed his microphone and shouted for Air Canada to go around. Up in the Airbus, the pilots slammed the thrust levers fully forward, aggressively pitching the nose into the dark sky, listening to the roaring engines desperately trying to arrest their descent. Flight data recorders would later reveal a truth that haunts aviation safety experts to this day. The Air Canada jet dropped to an altitude of exactly 59 feet above the ground before the engines could push it back up. The tail of a parked Boeing 787 is 55 feet tall. They cleared the parked aircraft by 4 literal feet. If that descending aircraft had continued its trajectory for exactly 3 more seconds, the kinetic energy of the impact, combined with the thousands of gallons of volatile jet fuel sitting on the taxiway, would have triggered a chain reaction fireball of biblical proportions. It would have undoubtedly been the absolute deadliest disaster in the entire history of global aviation. 3 seconds. That was the entirety of the margin between a routine night at San Francisco International and a world-altering catastrophe. This incident violently rewrote the rulebook on fatigue management, nighttime visual approaches, and runway lighting systems, because it proved that a perfect airplane flown by highly experienced professionals can still be drawn into a fatal trap by a single, unchecked assumption. The psychological weight of a cockpit emergency is impossible to replicate in a simulator. When an alert chimes, Human adrenaline demands immediate action. But there are moments where action without understanding is exactly what kills you. On a bright afternoon over the Indonesian archipelago, Qantas Flight 32, a massive double-decker Airbus A380, was climbing toward its cruising altitude. The A380 is a marvel of fly-by-wire technology, a massive flying computer network designed to cross-check every single system. But shortly after takeoff, the number 2 Rolls-Royce engine exploded. And just like the incident in Sioux City, it was an uncontained failure. Shrapnel ripped through the massive left wing with the destructive force of an anti-aircraft missile. But this aircraft did not lose just its hydraulics. The flying shrapnel severed massive electrical wiring bundles, ruptured highly pressurized fuel lines, and destroyed multiple independent hydraulic circuits. In the cockpit, Captain Richard Champion de Crespigny and his crew were not just facing an engine failure. They were facing an overwhelming avalanche of digital information. The electronic centralized aircraft monitor, the digital screen that tells the pilots what is broken, completely filled up with red warning messages. As soon as the crew acknowledged and cleared one page of catastrophic failures, another page immediately populated. They received over 50 discrete, terrifying system failure messages in a matter of minutes. The plane was slowly bleeding fuel from a massive hole in the wing, creating an extreme imbalance in the aircraft's center of gravity. The automatic braking systems were gone. The landing gear was heavily compromised. Standard airline pilot instinct is to put the plane on the ground immediately when an engine explodes. But the captain realized a horrifying truth. With a massive fuel load, no brakes, and unpredictable flight controls, landing right now would mathematically guarantee a high-speed crash off the end of the runway. In the midst of the deafening alarms and the screaming adrenaline, the captain made a brilliant, life-saving psychological choice. He commanded his crew to sit on their hands. He actually said, "We will not rush this." Instead of diving for the nearest strip of concrete, they kept the heavily damaged aircraft in the sky for over 2 agonizing hours. They manually calculated the shifting center of gravity. They manually calculated exactly how much braking force they could apply without blowing the tires and sparking a fire with the leaking jet fuel. They sifted through the noise of 50 different computer warnings, figuring out exactly which specific control surfaces were still connected to their side sticks. They treated the dying airplane not as an emergency to be escaped, but as a complex mathematical equation that had to be perfectly solved before they touched the ground. When they finally aligned with the massive runway at Changi Airport in Singapore, they brought the enormous machine down at an uncomfortably high speed. The tires screamed and deflated. The brakes glowed white-hot, exceeding temperatures of 1,000 degrees, stopping the massive airframe just mere feet from the end of the paved surface. Fire crews immediately doused the glowing landing gear in foam to prevent the leaking fuel from igniting. It was a masterclass in modern aviation survival. It proved an undeniable psychological law of the sky. When faced with an overwhelming cascade of mechanical failures, blind panic will always kill you much faster than a broken engine. Unyielding discipline, the ability to slow time down in your mind and meticulously work the problem, is the ultimate safety mechanism. But sometimes the threat in the sky is not loud. It does not come with shaking engines, shattering metal, or dozens of blaring red alarms. Sometimes the threat is completely silent, built entirely on polite conversations over a radio frequency. Imagine a heavy commercial airliner holding high above a storm-battered city, burning through its calculated fuel reserves. The pilots are heavily fatigued, frustrated by endless air traffic control vectors, watching the digital fuel totalizer steadily drop toward zero. They press the push-to-talk switch on the control column and transmit a seemingly clear phrase to the ground, declaring minimum fuel. To the stressed pilots in the cockpit, those 3 words carry the emotional weight of a desperate plea for immediate help. They are effectively saying, "We are running completely out of options. Please give us priority to land right now." But down on the ground, in the dark, heavily congested radar control room, The controller hears something entirely different. The controller is governed by a strict, legally binding operational manual. In the heavily regulated vocabulary of American air traffic control, minimum fuel does not mean emergency. It simply means the aircraft can accept little or no further delay. It is a courteous advisory. The controller acknowledges the minimum fuel call, but because the crew did not explicitly state the legally required word, Mayday, or declare a formal fuel emergency, the controller is not legally allowed to disrupt the approach sequence and move other aircraft out of the way. The airplane continues to be vectored through the thick, turbulent clouds. The pilots, constrained by cultural power distance and a deeply ingrained psychological reluctance to sound unprofessional or demanding, sit quietly as their engines begin to ingest the absolute final drops of liquid fuel from the wing tanks. The margin for survival is no longer measured in thousands of pounds of fuel, it is measured in mere seconds of thrust. The heavy machine is placed on a razor-thin edge. If they hit a sudden pocket of wind shear and are forced to execute a missed approach and go around, the high thrust demand of the engines will consume the final vapors in the tanks, resulting in a terrifying, silent dual-engine flameout over a densely populated area. They eventually make it to the runway, the wheels smashing into the wet concrete, and the engines spooling down with practically nothing left in the tanks. A tragedy was barely avoided, but it highlights the most chilling reality of modern flight operations. Words have mass. Words have weight. In the high-altitude environment of commercial aviation, precise phraseology is a literal tool of survival. When you're strapped to a machine flying at hundreds of miles per hour, your vocabulary must be as razor-sharp as the aerodynamic engineering of the wing. Because sometimes the difference between a safe arrival at the gate and a catastrophic headline is not fuel, it is the willingness to abandon politeness and forcefully demand the airspace to survive. When you strip away the massive engines, the miles of electrical wiring, and the incredibly complex flight management computers, you start to realize exactly what unites these four harrowing near disasters. The connective tissue of aviation survival always comes back to the intensely fragile, deeply imperfect human factor. A devastating disaster is never just bad luck. It is the direct result of a highly compressed, narrow window of time colliding with information overload. It happens when tired human brains make assumptions about a runway light, or when a crew allows the normalization of deviance to quietly strip away their safety margins, pound by pound, minute by minute, without ever speaking up. Every single time you walk down a jet bridge, take your seat, and buckle your seatbelt, your life is being suspended in the air, not just by aerodynamic lift, but by thousands of microscopic, invisible human decisions. The mechanics who torqued the bolts on the fan blades, the dispatchers who meticulously calculated the headwind fuel burn, the air traffic controllers separating tiny green dots on a glass screen, and the two professionals sitting up front behind the reinforced door, actively managing the relentless forces of physics. Most of those decisions, billions of them every single day across the globe, are perfectly correct. The system holds. The flight is boring, routine, and utterly uneventful. But true aviation safety, the reason the modern airline industry has achieved an almost mythical level of statistical security, was not built on the flights where everything went right. It was built in the agonizing, terrifying spaces between a shattered engine and a concrete runway. It was forged in the 3 seconds before a taxiway collision. It was written in the tense, sweating silence of a flight deck, managing 50 red alarms without a trace of panic. The sky above us is incredibly safe, but it is only safe because an entire global industry refused to look away, choosing instead to deeply, methodically learn from the horrifying moments that almost weren't.